Okay, in this presentation, we show some result of some explorations in the application of dimensionality reduction algorithms based on intrinsic dimension estimation on geomorphometric data. The point is that geomorphometric analysis, as we have seen in these days, generates generally a lot of variables. We have a very high dimensionality data set. This is related both to the fact that we have many geomorphometric variables to compute, as well as to the scale dependency in the calculation of geomorphometric features. And for example, related to the resolution of the DTMs, or for example, to the search radius of the moving windows. We have many reasons for this. Also, very often we combine geomorphometric features with other geoenvironmental variables, like for example, the ones coming from remote sensing imagery. And so the issues of high dimensionality in dataset is quite important. In fact, too many variables gives problems in the both unsupervised as well as supervised learning setting, increasing computational costs and often also decreasing accuracy. So in some way, it's worth to explore other ways respect to the classical one to reduce the number of variables and understand which features are relevant, which are not relevant or redundant. So from this perspective, the recent generalization and reinterpretation of the Morigita index with the work of Golay and Kanevsky is quite promising. Initially, the Morigita index was devised for the analysis of point spatial patterns. The main idea is to divide the space in blocks with a diagonal size delta, and to compute how many points in each blocks are present. And this permits using this equation, that is the classical Morigita index, to compute an index. If we compute this index for different sides of the block, we can have a curve that allows if the point pattern is clustered, random, or dispersed. But the interesting thing is that if we consider the classical Morigita index, or is a generalization, the multi-point Morigita index, and we plot the logarithm of the diagonal sides of the blocks versus the log of the Morigita index, we can find, for a given range of values of delta, a linear behavior. And the interesting thing is that the slope of this linear behavior is related to the fractal dimension of the point patterns, or more precisely to their intrinsic dimension. The good thing is that we can apply this approach in the geographical space, like in this case, point patterns, but we can apply this also in the variable space. So for the analysis of in the context of dimensionality reduction. Here is an example. Here we have a Swiss roll dataset generated by the function that you can see here from the R package ID mining. We can see that in this dataset we have 3 variables. So the Euclidean space dimension is 3. But if we apply the intrinsic dimension, we calculate the intrinsic dimension index, we see that the intrinsic dimension is 2 because the data lie on a surface. So at the end, the true dimension of the dataset is 2, not 3. And this is related to the fact that the X and Y coordinates are non-linearly strongly correlated. And so there is some redundancy between X and Y variables. So the main idea of these algorithms developed by Golay and Kanevsky is to use measure of intrinsic dimension in the context of dimensionality reduction. For example, if we are considering an unsupervised setting, we can detect redundant features, so variables that don't bring new information, variables that are not useful, simply trying to see if they contribute or not to the intrinsic dimension of the data set. If they do not contribute, they are redundant in some way. They don't bring new information. So they developed various algorithms, both in unsupervised as well as in supervised settings. And these algorithms are developed in the ID mining tools in R package. Currently, these algorithms work only with continuous variables, but in some way, these could be adapted also to categorical one. And in general, these algorithms are quite different, for example, from principal component analysis, in which dimensionality reduction is obtained with the definition of new variables, like the principal components. Here, an example, a basic example in an unsupervised context. Here we have, I computed some basic morphometric variables and a couple of Ragness-based indexes you calculate using the MED estimator, median absolute differences, for a quite large DTM derived from airborne leader. It covers more or less more than 6,000 square kilometers. And I considered 8 variables: elevation, slope, residual DTM, profile curvature, tangential curvature, plane curvature, anisotropy in roughness, and isotropic roughness. These 2 indexes of roughness are computed considering lag distances of 2 pixels, or are measure of roughness for very fine scale morphology. If we apply the algorithm to this 8-dimensional, from the Euclidean point of view, data set, we can see how the algorithm gives the result. It gives essentially a curve in which you have in the x-axis the features, the variables, and in the y-axis the estimated intrinsic dimension. And we can see, for example, in this situation, if you look at the red curve, that residual DTM as well as tangential curvature are in some way redundant. They don't contribute a lot to the intrinsic dimensions of the data that stabilize around 5.8. I also tried the algorithm on some sample of the data, considering only the 5% of the data. So the red line is referred more or less to 1 million points. Instead, the black curves are related to the 5% of this 1 million point. And it's good because the results are quite stable. And so this is a quite important technical characteristic of the algorithm. More interesting is to see how the intrinsic dimension and how the features selected change spatially. In this case, I divided all the study domain in tiles of 64 square kilometers, and I applied the approach for every tiles. And you can see here from this plot here, as the intrinsic dimension change obviously a lot from place to place. But for example, it's interesting to see that anisotropy in a short range roughness is a very informative parameter. And so this is a quite interesting result from my point of view. You can also apply this algorithm in a supervised setting, learning setting. In this case, I tried to build from real topography a synthetic data set, a quite tricky synthetic data set, in which the main idea is to have relevant features, input features, that are related to the output features in a non-linear way. And the other point is that these input features have a predictive power only if they are used jointly. The single feature is not informative for the output features. And moreover, these input features are linearly correlated. So for this reason, I used as output feature the slope computed with the simple formulation that you see here, and as relevant input features, the elevation on the 4 nodes. Then we generated other input features, irrelevant and non-redundant, and also another irrelevant features but redundant with the other one. Here you can see the scatter plot matrix of all the features. So we have 9 input features and 1 output features, which is the slope. And you can see that the relevant input features, the elevation of the 4 nodes, are also strongly linear correlated between them. The good thing is that the algorithm, if you look at this curve here, is capable to see that the relevant features that permit to predict slope are the 4 elevation at the nodes. From this curve, you can see which features contribute in reducing this index whose name is index of dissimilarity. And so only the features that contribute to reducing this index are relevant for the prediction task that we are considering. And so you see that only the 4 elevation contribute to the prediction of slope. And this is quite good because from the complex nonlinear relationship between slope and the 4 elevation at the surrounding nodes is not easy to be catched by predictive algorithms. So concluding, I think that these kind of algorithms are quite interesting in the context of geomorphometry as well as in remote sensing. I think that one of the critical points to be further investigated is related to the statistical shape of the distribution of the input features. Because when you have variables like the simple slope or roughness that have a high skewness, or you have variables like curvature that have heavy tails, it's clear that these kind of algorithms is sensitive to the statistical distribution of variables. And so it's very important the way in which you transform variables before doing the analysis. But this problem is common to many other statistical learning tasks like clustering and prediction. So is a kind of cures that we always find in this kind of approach. Now the study, the exploration is going on trying to apply this algorithm in the context of multi-scale analysis of roughness. So I finished my presentation. I hope to be in time.
Yes, you are.